Yeah, we are happy to have Ken Wood here on stage. We have seen a lot of people, a crowded booth, so yeah, really interesting demo Ken has shown at the Solution Expo. And Ken is working for Hitachi Vantara. So he's taking care of all the innovation around Pentaho and inside Hitachi. And if I got it right, you were working for 22 years for Hitachi, for a really long time. And Ken will talk about artificial intelligence, machine learning in combination with Pentaho. So Ken, thank you for having me here, and welcome to the stage.
Thank you. So both of my hands are busy holding things, so I don't know how this is going to work. I tend to be animated a little bit. Thank you for having me. Thank you for listening. Some of the people that have been around the booth, I haven't showed you all the demos because I kind of was hoping to save it for now. So I hope there's still some surprise coming. Real quick, not that I want you to follow me, but if you follow me, we'll be posting some things to Twitter from the demo, and you'll be able to see some of the things that we're doing through that. Or you can just follow the hashtag PUM19. I do need to make some apologies. My slides are in English, so I don't know German, I don't speak German. I do have an accent, I apologize for that. And I apologize that I also talk fast. And I'm going to go faster because this is usually an hour-long presentation that I compress down to 20, 25 minutes.
30 is fine.
30 minutes with the demos and maybe some questions. So unfortunately, it might go fast. So if you want to, we can talk later at the booth. So I'm Ken Wood. 2 words, not the same as the stereo brand. And I run Hitachi Vantara Labs. Formerly Pentaho Labs. So last year they changed the name on me from Pentaho Labs to Hitachi Vantara Labs, which is confusing because people think I have a laboratory full of hardware equipment as opposed to we do R&D for Pentaho and related subjects. What I refer to as RD&I. So research, development with a little d, we don't make product, and innovation. We do prototypes, we do experimental capabilities in and around the Pentaho suite of tools. And lately what we've been doing for the past 18 months is bringing more and more machine learning natively to Pentaho, and I'll explain what that means. More importantly, it's basically trying to make machine learning easier to use. Not easy to use, easier. It's still hard, you still need to know what to do. And advancing the data science capabilities from Pentaho, or in Pentaho. And more importantly, what I like to say is expand the types of use cases that Pentaho can address. So it's very ETL oriented, a lot of ETL use cases being used, data integration, all the good things that Pentaho does, but streaming, IoT, analytics, AI, that's sort of the things we're trying to expand to let you know that Pentaho can do a lot more. So show of hands, who in the room is a data scientist? Yes, good. Who wants to be a data scientist? Okay, perfect. I'm neither. I'm a technologist. So I basically take technology that smarter people create, and I tell stories with it. I integrate it, I make things work, I do demos, I tell stories, I make the other guys look really good. So, to get right into it, when we talk about doing machine learning, AI is just a broad category of a lot of different technologies to make things look intelligent. Today, there are basically 2 ways to do machine learning, which is a subcategory or subdomain of artificial intelligence, in Pentaho. The first method we did was bring your own code. All right, so recently a Python executor step, previously an R executor step was all setting up a microserver within the environment and the ability to run code within that step within the data flows that you can do with PDI. What we've been working on is, again, making machine learning easier to use with no coding, with a feature or an experimental feature we call PMI. And as you can tell, the P should have been Pentaho, but we can't call it Pentaho now, so we used to call it, or we call it plug-in machine intelligence, or you can say PDI machine intelligence. And the word or the term machine intelligence, if you look it up, particularly in and around Google research, machine intelligence is not just machine learning. It's all about machines being intelligent, not just training, not just testing models, but actually putting models to work, doing things with the models, solving problems with the models, taking it beyond the experimental phases. So I like the term machine intelligence versus just machine learning. In and around, say 2014, 2013, we introduced, and this is before I was in labs, introduced the data science pack. And that was where the R executor step came from, or was introduced, excuse me, and as well as a couple of WECA steps. PMI technically is supposed to be the data science pack version 2, or volume 2, or and so forth, but we didn't call it that way, so we just came up with PMI. PMI, you gotta remember, is just probably gonna be the lab's project name. If it ever becomes a product or included in the distribution, it'll probably get renamed to something else. Hopefully I'll have a say in what it's called. And part of PMI, a lot of what PMI has enabled is a lot of the talk around machine learning model management. We make that capability easier, but it still requires PDI to interpret the results so that you can manage the models. So a lay of the land, as I mentioned, artificial intelligence is a broad category of subdomains. Natural language processing, emotional processing, vision, speech, robotics, and so forth. Machine learning is just one of those subdomains. It in and of itself is very popular, very broad in its scope. And in fact, deep learning used to also be a category or subdomain of artificial intelligence. But really, when we started working with it, it turns out it's just machine learning, and in fact, it's supervised machine learning. So of machine learning and the subdomains within machine learning, you have supervised, which means you already know the answers. You have historical data and you know the answers to your problems. You're going to train a model to recognize the patterns. And then you're going to forecast or predict what future answers will be that you don't know. That happens the same way with deep learning. There is unsupervised learning where you don't know the answers. You don't even know what the labels are called. So all you can do is really cluster, associate, anomaly detect with those models. The reason they're highlighted, supervised, is that's what we're currently doing in PMI today. We do plan on doing some unsupervised, but we're not there yet. And there's some other facets, a little more specialized, semi-supervised, and reinforcement learning you see in gaming a lot, basically goal-oriented, with feedback into the models to improve the answers. So today, we've been working with PMI now for 18 months. Probably late last year we introduced a new version, 1.4. Again, it's just experimental. In the marketplace, you can get it out on the marketplace. We include 5 machine learning execution engines. Scikit-learn from Python, MLR from R, MLlib from Spark, WECA, and GL4J. Those combine into what's currently PMI. But PMI in itself is a framework. In fact, it's a framework built to be extensible. We can add algorithms. So once you plug in this plugin, you can add more plugins. So plugin of plugins for more algorithms, and a framework of frameworks, so you can add more ML types. The next ML type we'll add is unsupervised. So we'll end up with another framework like this for unsupervised. Careful. Too close to the speaker. So what happens when you make machine learning easier to use? It's not quite easy. You still have to know what you're doing. But the way we set it up, all the defaults run. You will get a model at some level of accuracy, and then you can tune. And that's where sort of more seasoned data scientists will go in there and start tuning parameters within the algorithm themselves, albeit visually. When it becomes easier to use, domain experts can now apply machine learning. They don't have to really know how to code. They can apply a machine learning algorithm to some data they have. So a doctor might be able to use it, not a computer scientist. Other domain experts can start looking at it as applying machine learning to their problems. Data engineers do all the hard work. They do all the data prep, all the data collection, all the feature engineering. They can now take it to that next step. Let me add an algorithm and see what my answers are. All right, and possibly work with a data scientist to start improving those answers or those accuracies. Increase the productivity of data scientists. Right now they spend a lot of time writing code. Well, if you could fail fast, fail cheap, fail productively, you can actually increase the productivity of these very expensive assets or resources. Okay? We actually call this kind of a use case for this machine learning model exploration. You can build a whole lot of different models from the same data set. Using PDI, you can create a data flow, one data flow, and use Python, use R, use Spark, and create models from algorithms in those. So it's very streamlined, you can fail fast, you can try a bunch of different iterations, and once you decide this is the best performing library algorithm on this data, then you can go write code. If that's what you have to do to get into production is write code, at least you have a starting point, and you can do it in an hour. So when the complexity has now been moved away from machine learning, the complexity is now back in the data prep. I spend a lot of time preparing the data so that I can ask the right questions, right? The easiest question to ask of a model or of data is yes or no, true or false, up or down. Two classes, binary classes. So if you can position the data in, is this a fraudulent transaction based on all this data, or not, fraud or not fraud, then you can actually put the data in that position and build a model to recognize fraudulent previous or historic fraudulent transactions so that you can predict future transactions that are fraud. It gets harder, obviously, with multiple classes. I do get asked the question quite a bit, what is the difference between machine learning, or in this case, classical machine learning, and deep learning? And to me, it boils down to a best practice. Typically, classical machine learning is best suited for data or structured data, so records, CSV files, database queries, and so forth. While deep learning is best suited for unstructured data, images, audio, possibly video. Video being a series of images. So it is a best practice. There are some algorithms that we have exposed from the deep learning library, DL4J, that do normal or classical machine learning algorithms, and you can force some unstructured data through vectorization of text, for example, and run it on machine learning, classical machine learning. So you can do one of each, but they're best suited for deep learning on unstructured, classical machine learning unstructured. And one of the powers or unsung heroes of PMI is the uniform evaluation metrics that we present. So every engine, every algorithm in those engines come out with these metrics, and the bottom dozen are for every possible class. So you can end up with hundreds and hundreds of metrics that come out to indicate the accuracy of your model. So when you actually test it, you'll get an accuracy. I like to use the kappa statistics. That is a very good overall indicator of how accurate the model predicted what you tested with. So you train a model, and then it tests itself. And it was 95% accurate, or something like that. You can use these numbers, these metrics, to compare models. And that's the power. No matter what engine you use, no matter what algorithms you use, you can actually compare the results from the same data set. So decision tree classifier and Python and the decision tree classifier from Weka, if you had to code the metrics coming out of there, it's a lot of work to get them to be uniform and comparable to each other. These come out automatically from the PMI framework. And that's where you see a lot of the champion-challenger strategy in and around model management. So we can actually create an arena of different models and compare them to each other. I'm not going to go into the champion-challenger strategy. That's one of the slides I pulled to make this shorter. But the whole idea around model management is this flow of prepare the data, engineer the features, train the model, deploy the model, but then continuously evaluate, monitor, look at the performance of the model. So why would you do that? The notion of a model degrading comes up. It's no longer as accurate as when I first built it. For some reason, the performance or the precision is degrading. We deployed it because it was 93% accurate in detecting fraud. 4 months later, it's only 80% accurate. Did the model change? No. What happens? The data changed. You trained it on historical data to detect fraud in this fashion. Well, guess what? Bad guys, once they figure out they can't fraud anymore, they can't steal from you anymore, are going to change the way they fraud you. That means your model worked, first of all. If it degrades, they're doing something different. That means your model, your strategy worked. But your model is no longer working. The data pattern, the nature of the data changed. You have to do what? Evaluate it, retrain it, trigger a retrain, maybe the new data, you can train it on the new data, or possibly another model will perform better on the new data pattern coming in. So a degraded model is not an indication of something bad going on. It means you worked. You just got to keep up with the times. And that's what this model or this strategy is about, is constantly evaluating, possibly even replacing or retraining models as thresholds are met. So you kind of want to keep that policy in place where your accuracy is at a certain level. And at least be warned that the accuracy is going down and you need to either manually retrain, or we can, with PDI, we can automatically retrain or replace models in production. And again, it's all experimental. We haven't actually had a customer do this because this isn't supported. That's why we look at the model, machine learning model exploration as a use case. But this actually works with other strategies where we use the Python step and only algorithms within Python. Since that is a supported capability that gives you some machine learning in it. Eventually, Pedro's going to decide this is a great idea. We'll put it into the product. So people wonder, before I get to this slide, people wonder what is the method for things from labs, these experimental capabilities that we make available for you to try out and test, educate yourself. When does it get into production? When does it become a product? When does it get supported? And a lot of it starts out that way. We put something out in the marketplace or out in the community, and you try it out. You like it. It gets momentum. You know, customers want it. And so product management, possibly even product marketing or the sales team get this feedback, and it goes back into the product engineers, and eventually they'll make a decision, this needs to be in the product. MQTT is a good example of that. That was probably the fastest thing that we put out that eventually became a product. It took less than, it feels like 18 months. So what are some of the possible use cases, particularly around deep learning with unstructured data? So I'm going to show you a couple of examples, a couple of demos, but basically any kind of pattern in images. Somebody once asked me, can you detect leaks at a refinery or a sewage treatment plant? Well, yeah, the default sensor at a lot of these plants is video. So you can actually there's video of all the equipment and all the plumbing, and there's pictures of what no leak looks like, and what pictures of a puddle looks like. So at least if you see a puddle or detect a puddle, you can at least warn somebody, maybe not evacuate the building, but at least say, hey, go check this out. There's something wrong at this location, possibly leaky pipe or it's raining. So things that you can look at, think image, think differences in images, things that you can train and detect anomalies with. Again, the easiest one is leaking, not leaking. So what are we looking at? Since we don't make product, we don't have a roadmap. There's no schedule to anything, we have vision. We look off and say, oh, this looks cool. We're one of the few organizations in the company that gets to say, let's go play with this, this is cool. No, there is some method to the madness in that we kind of listen to the industry, and everybody's trying to get into what is deep learning, how do we use deep learning, for example. Some of the things we're looking at, there's no particular order of priority, but one of the things we started noticing is as you start doing data science with Pentaho, the visualization of the data needs to look different. Most data scientists will do these scatter matrices. So it's a pairing of every possible point of data in a matrix of charts. We can't do that. We do charts one at a time. So we're looking at doing some visualization. I'll have a demo of that. We're looking at a new algorithm that can actually infer on a GPU. Deep learning trains on a GPU. So when we train models with deep learning, we're actually, if there's a GPU detected, we'll do it on a GPU. So either on your workstation or in a server. If it's NVIDIA and you use CUDA as the API, we'll train on it. And in fact, there is a little bit of pre-processing and even image processing during inference on a GPU. But we're looking at ways of leveraging that accelerated hardware in inference time. So image training is interesting, but inferencing is production. You're actually doing something with a model. And most models, machine learning or deep learning, typically infer on a CPU. This is an interesting algorithm in that if you train it on a GPU, it's structured data. If you train it on a GPU, it will execute on a GPU. So we're looking at that. We mentioned the supervised machine learning where we can do batch clustering, and we're looking at algorithms in and around doing anomaly detection on the edge. So we'll be able to run this on an edge device, possibly on a Raspberry Pi, for streaming data, doing anomaly detection in real time. We're probably going to go with the Keras engine as a sixth engine within PMI, mainly so that we can access TensorFlow. And then transfer learning. Transfer learning in deep learning is reserving some layers of the neural network. You train the model, you test the model. These are very expensive to build, they take a long time. You reserve some layers, and if the model is not accurate, you throw some new images at it, and now you add to the training. You continue the training or resume the training of the model with different images. It's called transfer learning, where we think we can do that, and it may be just a matter of exposing some capabilities. So concepts to consider that we're looking at. I've started a blog series in and around interpreting or extrapolating hidden results. And I've shown some of you some of the examples at the booth that a yes or no answer has other answers. There may be a question about in-between answers. You're always going to get one or the other. You're never going to get a pure tie. So when you go for max prob on a yes or no answer and it says yes, and it's 51%, that's probably an I don't know. Okay, so you want to get this even a binary class at least has 3 answers. And so we're looking at that. And then the combination, when you start looking at multi-class problems, now you're actually looking at classes where there may be 3 or 4 answers, legitimate answers. Even though you want one, there's a combination there, and you have to interpret it. We are doing one probability, but technically we're running into this problem where it sees 2 answers or 3 answers. Something I call broad spectrum learning, or deep learning models, or junk drawer models. So right now, You can have thousands and thousands of images in one monolithic model. Why not create a broad spectrum model of a bunch of different objects and then create a decision tree out of that model for more specific analysis? So, broad spectrum analysis, cars, flowers, food. You determine its flowers, go into a deep learning flower model and tell you what flower it is. Rather than try to get every flower in there, every car in there, every food in there, and coming up with a 102 or 200 class model, which is very hard to manage. Just an idea, we're looking at that. We think we can do that just with PDI and PMI. Ensembles is the new trend, or it's a trend that's going on where you actually have multiple models, and again, different models are better, different engines are better, where they vote on the answer. Some of the most accurate predictions today, either through Netflix, X-ray analysis, chest X-rays, are using these ensembles of models. 4 out of 5 models say this is cancer, rather than one model saying it's cancer. Is a better and more accurate way to predict something. So we're looking at voting systems, voting models. But those are things we're going to try. It's a lot of work. So we'll see when it comes out. All right, I'm going to try to do some demos for you. After lunch, or after the first session, the network kind of acted weird, so I don't know if this is going to work or not. Can you still hear me? Okay, so I mentioned data science, data visualization. So we're looking at adding some new visualizations within the tool itself, so data scientists can stay in the tool, do their data integration and their data science. So here's a data set. You can get it off the internet. It's called Segments. It actually has 7 classes, and it's trying to predict what the surface of this picture is. So you'll see path, foliage, grass, brick face, windows, glass, and so forth. This is what the data set looks like, but let's visualize it. So this is the the way this data looks like. Let's see. As we can explore it just off the default, but if we were to start highlighting this, saturation, we can add some color and some interesting clustering, not machine learning clustering, but visualizing the data. We can actually see these clusters of classes in here. You can zoom in, what I call fly through your data. You can see there's a legend. Of the classes themselves. So the colors mean something. Some red is cement and so forth. If this didn't mess up, you should be able to all right, the pop-up. If you hover over any data point, you'll get a pop-up of the actual data itself. And right now that is not working. That's why it's still experimental. And we can now produce the scatter chart, the scatter plot, or the matrix charts that data scientists want to see. So these are basically 2D representations of every pairing of data in these charts. that is useful for experimenting with the data, looking at what the data characteristics are before you start creating your models or start engineering features into it. So you can even see, in this case, these are essentially 2D representations of the 3D plot that we just did. You can see the clustering, you can see the histograms here, and we can actually export this. We can export it as an image, or I think we can export it as some other data type, I forget what it was. But we can save it as an image and export it as an image. And again, this is just the perspective. So we can get back to where we started. Okay. So, there's a demonstration we did in and around using deep learning for analyzing X-rays. When we did it, it was only based on physical X-rays. So we would actually insert an X-ray in an X-ray viewing machine, speak to the device, analyze the X-ray, and it would speak the results. And that's some of the other capabilities we're looking at adding to Pentaho is speech, text to speech. So we actually create a step that you can enter text or get text from the field and have it speak the results. Because explaining the probability distribution on a chart takes about 5 or 10 minutes to explain why this is an elbow. Okay, so why not just have the results spoken to you? So let's try this. This is new Hay Ray, or what we call Hay Shin Ray. I don't have physical X-rays. My screen is back there unplugged. I don't have a third plug. But we can at least now, instead of using physical X-rays, we can grab images from a photo library that we've either taken previously or downloaded from the internet. This one always works.
Okay, I will send this X-ray to the Pentaho server for analysis.
It should be nice and warm. So this is actually going through the cloud out to a laptop and back. I keep meaning to add an indicator that it's online. I hope nobody closed the laptop. That's the problem with the live demo, right? Okay. Please come to the booth. I'll fix it. What this will do is it actually analyzes the X-ray. It actually sends it to the Pentaho server, which has two models. The models are injury detection, and that is the premise of a challenge from Stanford around 14,000 X-rays, is to detect whether a body part or an X-ray has an injury associated with it. We've extended that to also include a model that is a 5-class model that detects the body part. So this will actually tell you what this is. It is a humerus, and it has an injury. And then it goes on and asks if you'd like it to schedule an appointment for you. I'll check what's going on over there. I've had a couple network issues today. We can store this. This actually will store it to HTTP. In the process, it creates a movie. So the audio files, the text files of the analysis, and the image are combined into a movie. And we save that all into HTTP as well as custom metadata. As part of the analysis, we create an XML file. And that XML file is ingested into HTTP as custom metadata for searching later. And once that's all done, we can actually tweet this. It'll tweet the movie and a bunch of hashtags and some things, and some of you might have seen that. Later today, I'll fix that and we can actually look at some of these. So I apologize that it's not working. But it is easier to travel with. So I think that's all I had for now. We can do some more demonstrations back at the booth, but at this point, are there any questions? All right. Thank you so much.